Accelerometer. Accelerometer is a sensor inside your smartphone that detects motion and orientation. It works by measuring the force acting on the phone in 3 directions: left and right, forward and backward, and up and down. When the phone moves in any of these directions, the accelerometer detects that movement instantly. This is the sensor responsible for rotating your screen. Hold your phone upright, the screen stays portrait. Tilt it sideways, the screen switches to landscape. That switch happens because the accelerometer detected the change in orientation. It also works in fitness apps. When you walk or run, every step creates a small physical movement. The accelerometer counts those movements and converts them into step data. But the accelerometer only detects movement. It cannot tell where the phone is located. That is a different sensor entirely. Gyroscope. The accelerometer detects movement, but it cannot detect rotation precisely. That is where the gyroscope comes in. The gyroscope measures how the phone rotates around its own axis, not just which direction it tilts, but exactly how fast and how far it rotates in any direction. The difference becomes clear in gaming. In a racing game, tilting the phone slightly to steer works through the accelerometer. But in a first-person game, where you physically rotate the phone to look around a scene, that is the gyroscope working. The accelerometer alone is not precise enough for that level of control. The gyroscope is also what makes 360-degree videos work on smartphones. As you rotate the phone in any direction, the gyroscope tracks that rotation in real time and adjusts the video view to match exactly. Proximity sensor. The proximity sensor detects how close an object is to the front of the phone without any physical contact. It works by emitting a small infrared light beam from the front of the phone. When an object comes close, that beam reflects back. The sensor detects the reflection and registers that something is nearby. The most common use is during phone calls. When you raise the phone to your ear, the proximity sensor detects your face and turns the screen off immediately. This prevents your cheek from accidentally tapping buttons during a call. As soon as you lower the phone away from your ear, the sensor detects that your face is no longer close, and the screen turns back on. Without this sensor, every phone call would risk accidental touches on the screen from your face. Ambient light sensor. The ambient light sensor measures the brightness of the environment around the phone. It continuously reads the light level in the room or outdoors. When the environment is bright, like direct sunlight, the sensor signals the display to increase brightness so the screen stays visible. When the environment is dark, like a bedroom at night, it signals the display to dim down automatically. This is the sensor behind auto brightness. When auto brightness is enabled, the phone is not guessing the right brightness level. It is reading the actual light in the environment and adjusting accordingly. Without this sensor, the screen would stay at a fixed brightness, regardless of conditions. Too dim outdoors. Too bright in a dark room. Fingerprint Sensor. The fingerprint sensor reads the unique pattern of ridges and valleys on your fingertip to verify your identity. There are 2 main types used in smartphones today. The first is the capacitive fingerprint sensor, found on the side or back of phones. It works by detecting tiny electrical differences across the surface of your fingerprint. Ridges make contact with the sensor, valleys do not. That difference creates a unique electrical map that matches your stored fingerprint. The second is the optical under-display fingerprint sensor, found on most modern Android flagships. When you press your finger on the screen, the display emits a brief flash of light. That light reflects off your fingerprint back into a camera sensor beneath the panel. The camera captures the fingerprint image and compares it to the stored one. Optical sensors allow manufacturers to place the sensor anywhere under the screen, making the front of the phone completely clean. Face ID and 3D face recognition. Face recognition on basic phones uses only the front camera. It takes a flat 2D photo of your face and compares it to a stored image. Because it is only a photo, it can sometimes be fooled by another photo of the same face. 3D face recognition works completely differently. Apple's Face ID uses a dot projector that fires over 30,000 invisible infrared dots onto your face. An infrared camera then reads how those dots land across the surface of your face, capturing the actual three-dimensional structure of your features. This depth map is what gets compared during authentication. Because it reads actual depth, not just a flat image, a photo of your face cannot unlock it. The sensor physically cannot match a flat surface to a three-dimensional depth map. This sensor cluster is why the notch or dynamic island exists on iPhones. Barometer. The barometer measures atmospheric pressure, the weight of the air around the phone. Atmospheric pressure changes with altitude. Higher up, pressure drops. Lower down, pressure rises. The barometer reads these changes and converts them into altitude data. This is why GPS on a smartphone can tell you not just where you are on a map, but which floor of a building you are on. GPS satellites provide horizontal position. The barometer provides vertical position. It also assists weather apps. A sudden drop in atmospheric pressure typically signals that a weather change is coming. Without a barometer, indoor navigation and floor-level altitude accuracy would not be possible using GPS alone. GPS sensor. GPS, or Global Positioning System, is a sensor that determines the exact location of the phone on Earth. It works by communicating with satellites orbiting the planet. The phone receives signals from multiple satellites simultaneously. By calculating the time it takes for each signal to arrive, the phone determines its distance from each satellite. Using the distance from at least 4 satellites, it calculates the precise location. This is what powers every navigation app on your phone. Google Maps, Waze, ride-hailing apps, delivery tracking. All of them rely on GPS to know where you are in real time. GPS works best outdoors with a clear view of the sky. Inside buildings, signals weaken because walls block satellite communication. And because communicating with satellites is power-intensive, your phone does not rely on satellites alone. It uses something called assisted GPS, pinging nearby cell towers and Wi-Fi networks to estimate your position faster and with less battery drain. Hall sensor. The Hall sensor detects the presence of a magnetic field near the phone. It is a small and simple sensor, but it handles one specific task very efficiently. When a flip cover or folio case with a built-in magnet is placed over the phone, the Hall sensor detects that magnet and signals the phone to turn the screen off. When the cover is opened, the magnet moves away, the sensor detects its absence, and the screen turns back on. This is why smart covers work automatically, without pressing any button. The phone is not detecting the cover physically, it is detecting the magnet inside it. Ultrasonic fingerprint sensor. Optical fingerprint sensors use light to scan your fingerprint, while ultrasonic sensors use high-frequency sound waves. The sensor sends sound pulses toward your finger, which bounce back differently from the ridges and valleys of the fingerprint, allowing it to create a detailed 3D map of the print. Because it relies on sound rather than light, it can still work when your finger is slightly wet or dirty, whereas optical sensors often struggle because moisture scatters light. However, very thick screen protectors can interfere with these sound waves and reduce accuracy. This technology was developed by Qualcomm and has been used in Samsung's Galaxy S and Galaxy Z series since the Galaxy S10, and it remains one of the most accurate under-display fingerprint technologies in smartphones. Magnetometer. The magnetometer detects magnetic fields around the phone by measuring the strength and direction of the Earth's magnetic field, allowing the device to determine which way it is pointing relative to magnetic north. This is the sensor behind the compass on your phone, and it also helps navigation apps like Google Maps show the direction you are facing. Without a magnetometer, your phone could still show your location using GPS, but it would not know which direction you are facing, making navigation far less useful. Every sensor in your smartphone was built to solve a specific problem, and most of the time, you never notice them working, because that invisibility is exactly the point. If you want more smartphone and tech videos, explain this simply. Subscribe. There is a lot more on the channel.